All right, so last week we talked about least squares, and we're going to continue that discussion today. So if you remember, we talked about linear least squares, or least squares estimation for a linear problem, where the problem of interest was of this sort, and the only thing that we assumed was that this W was zero mean. Okay. Aside from this, we didn't make any distributional assumptions, and the cost function that we minimized was the following. Okay, and another way to write this, of course, is this is the norm of x minus h theta squared, or the Euclidean norm, 2 norm of x minus h theta squared. And x minus h theta is the error, so you're minimizing the square of the error, and that's what the name least squares implies. Okay, so if you remember, when we minimize this with respect to theta, the solution that we obtained was this: H transpose H inverse, H transpose S. So this is the standard linear least squares solution. And a slightly more general version of this is also true. You can also compute what's called the weighted least squares. It's very much like this, except that the J also includes a weight matrix, W x minus h theta. Okay, so this W here is a symmetric positive definite matrix. And what it allows you to do is allows you to give different weights to each one of the pieces of this error. So if you think of this h theta as a vector and think of x as a vector, then there's x1, x2, up to xn. So each component has its own error that you can define, element by element. And so what this W allows to do is to assign different weights to each one of those components. So some components may be more important, you give them more weight. Other components may be less important, you give them less weight. So the idea here is that if this W, as I defined it, is symmetric positive definite, then you could write x minus h theta times W. You could write this as a square root. Okay, so W could be written as, let's say, d transpose d, and then you could write this as d transpose d times x minus h theta. Okay, and now if you take this and take this together, there's a transpose here. Okay, you can absorb this d inside here and basically write this as something that looks very much like what you had before. Okay, so if you absorb d inside the definition of these guys, so that this basically becomes dx minus dh theta transpose, and then here you have dx minus dh theta, and then you define dx as x tilde, you define dh as h tilde times theta transpose x tilde minus h tilde theta. This looks exactly like what you had up here. So you just transform this more general formulation into the standard formulation, and then you minimize this with respect to theta, and then you plug in what h tilde and x tilde are, and what you obtain is the weighted least squares solution is simply h transpose w h inverse h transpose wx. Okay, so the only difference between these two solutions, the standard least squares and the weighted least squares, the only difference is this matrix W. Okay? You might also remember that if we, in fact, assume that W has a covariance matrix, which is C, let's call it C, then, so let me write this down, if the covariance of W is C, then if you simply let this, okay, I'm confusing you with little w here and big W here. Sorry about that. This is the covariance of this guy. Okay? So if this is C, then W here, this big W here, simply plays the role of C inverse. Okay? So this weight is simply C inverse. And then this estimate then basically becomes what you had before, which is the minimum variance unbiased estimator when the noise here is Gaussian zero mean with covariance C. This is from a couple of lectures ago. Okay, so going back to this, just to remind you, least square solution coincides with the maximum likelihood solution when the noise is Gaussian zero mean. Okay, and that also, of course, coincides with the minimum variance unbiased estimator. Again, if the noise is Gaussian. But in order to arrive this, the only assumption we made was that the noise was zero mean, period. Okay? All right, so now I want to give you a little bit different perspective on why the answer looks like this or like this by talking a little bit about the geometry of the least squares problem. Okay, first of all, let's write the model again. Okay, so here's the signal, right? Let's call that S. It's a vector S. So what you notice from this model is that this signal is not some arbitrary function you're trying to estimate. In fact, S is a signal that lives in a space defined in this particular way. So you have S equals H theta. Now we can be a little bit more explicit about the way we write this. We can in fact write H in terms of its columns. So we can write it like this. S equals H1, H2, and so on. Let's say HP. And then a bunch of coefficients here, theta 1, theta 2, to theta P. Okay? Now, of course, another way to write this is this is a sum, I equals 1 to P, this little p of theta I, HI, where these HIs are columns of H. Okay? All right, so if you look at this, what this is telling you is that the signal you're going to be looking for is not just some arbitrary signal, it's a signal that lives in a space that is spanned by the columns of H. Okay? So let me write this in a different way. So this is a span of H1, H2 through HP. And another way to just write this is to write it H1 through HP with a capital S defining the span. So in terms of a picture, this is what it looks like. So I'm just going to draw a two-dimensional version of this. Suppose you only had two of these. Then what you have is a couple of vectors, let's say h1 and h2. Okay? And these two span this two-dimensional space. And this is where S lives. So this is this set. Okay, now let's go back for a second to this measurement equation. Now if you look at this measurement equation, this part of it, of course, lives in this space. Right? But now you're taking this signal and you're adding some noise to it. And this noise has some distribution. It's a random quantity. We haven't really made any assumptions about what it is. But one thing we can be sure of, almost sure of, is that whatever this W is, the likelihood of the sum of these two terms still living in the space is almost zero. Right? So one of the things this noise is going to do is it's going to take the signal vector and pop it out of the space. Okay, so X is not going to be sitting necessarily in the space. It might be sitting somewhere outside the space. So this might be X. Okay? And let's say for the sake of simplicity, I just center it at somewhere, and let's call it the origin. Okay. So now, if I look at the minimum of the least squares criterion, what I have is I want to minimize over theta the norm of x minus h theta, right? And this is theta hat least squares. Okay. So if I minimize and I get this, then what is the least squares estimate of s, of this s? That's easy. It's h times theta hat least squares, right? Okay. In other words, once I find the least square solution, all I have to do is multiply it by h, and then I get a signal that lives in this space. Okay. All right. So let me draw. Whatever this estimate happens to be, there's going to be some error associated with it, right? So let's write E equals x minus h theta hat, like that. Okay. So now let's so remember this is s hat. Okay. So let me draw an s hat here. So let's kind of be a little bit crude about this, and let's say my s hat is this. Okay. Okay, if this is my s hat and this is x, then the difference between these two things is going to be this vector here, right? Okay, so this is the epsilon. All right, and this epsilon is, of course, what I'm trying to minimize here. The norm of this is what I'm trying to minimize. I forgot the square. Okay. So if I look at this picture, basically my task is to find an s hat such that the length of this vector is as small as possible, right? So by just looking at this picture, how would you pick this vector epsilon, or better yet, how would you pick s hat? Intuitively. Perpendicular, right? That's the smallest distance to this space is a perpendicular line. So you wouldn't pick s hat to look like this. Instead, you would pick your s hat to maybe come straight down. You would pick that as your s hat, and you would pick this angle such that this angle is 90 degrees, right? Okay. And so this is the epsilon that would be the smallest epsilon you could do. Okay. So intuitively, this is pretty clear. Now let's write down what this means from the point of view of linear algebra. Okay, so what we just convinced ourselves of is that the minimum error occurs when epsilon, this error, is perpendicular to the space spanned by the columns of H. Right? Okay, so how do we write this? This is, remember, x minus h theta, or x minus h theta hat. So this is x minus s hat. In order for this to be true, I want this to be perpendicular to hi for all I equals 1 to p, right? is if the error is perpendicular to the space, then it must be perpendicular to all the vectors that span the space. Right? So I write this down. And another clean way to write this is x minus s hat transpose times hi is equal to 0 for I equals 1 to p. Right? And shorthand way of writing this, x minus s hat transpose times h1, h2, hp is equal to 0. Okay, this is now the whole matrix H. So x minus s hat transpose times h is equal to 0. Rewrite this, x minus h theta hat transpose h is equal to 0. Okay, simplify again, you get well, simplify a couple of steps. X transpose h equals h transpose x equals h transpose h theta hat. Okay, and this is what we showed you earlier as what I call the normal equations. And normal is another word for perpendicular. So the reason why this is called the normal equation is because of this orthogonality constraint. So we didn't use any statistics, we used purely just geometry here, linear algebra, to come up with this equation. Now of course if you solve this for theta hat, you get theta hat equals h transpose h inverse h transpose x, which is in fact the least squares solution. Okay? Now with this in hand, if you also wanted the least squares solution for S, which is this product, then that would be H times H transpose H inverse H transpose X. Okay? Any questions about this so far? All right. So if we rewrite this here, the least squares estimate of the signal H transpose H inverse H transpose X. This guy here in front is a matrix that we talked about a little bit before. I'm going to call it capital P, so I'm going to write this as P times X. It turns out this P is something called a projection matrix. And the reason why it's called a projection matrix is, well, it satisfies a couple of algebraic properties. So P transpose is equal to P, so it's symmetric. And also P transpose times P, which is P squared because of the symmetry property, is equal to P, capital P. So this is what we called idempotence. In other words, if you apply it once, then its work is done. If you apply it again and again and again, it doesn't do anything. And the reason why it doesn't do anything is this. What the matrix P is doing is it's taking this X and projecting it down to the space. It's an orthogonal projection of the vector X onto the space spanned by the columns of H. So once you've projected down, you're done. Yeah?
One simple question. On this page.
This page.
I think it was a little below that. You do H transpose H theta hat equals H transpose X.
Here?
Yes.
Uh-huh.
Now, with matrix operations, can't you just eliminate that H transpose from both sides and then...
No.
Why not? What am I forgetting?
You want to eliminate this H transpose?
Yes, and then the detector basically becomes...
How would you eliminate H transpose?
I mean, you're doing the same operation to both sides of the equation, so...
Okay, this is a basic linear algebra question, so let's take it after class. Okay? You cannot eliminate this H transpose. This H transpose, first of all, is not a square matrix. right?
Oh,
H is like this. Okay?
okay, that's what I was forgetting.
All right. Okay, so this matrix P is a projection matrix. So remember here we have more measurements than we have unknowns, right? So this P, what it's doing is it's projecting your data vector X onto the space of where the signal is going to live. And also this P is going to have rank equal to little p, right? Rank of this capital P is equal to little p, and this is the number of parameters. Oh, Jesus, sorry. All right, the number, this little p is the number of free parameters, which is in that theta, okay? All right, so if this is true, then we can think about what the minimum of this cost function theta is. So if you remember, this turned out to be X transpose times I minus H transpose H inverse H transpose X, and we wrote this as X transpose QX. This was from last time. And this we can write as X transpose I minus PX with this P that I just defined here. Okay? Q was also a projection matrix. Right? So Q and P are in fact called complementary projections. So X transpose minus X transpose times I minus P times X, this I can write as X transpose X minus X transpose PX. This is the norm of X squared minus the norm of PX squared. So if you look at the geometry, what we have, again, if we look at this, you have X here, then you do an orthogonal projection of this guy. It's 90 degrees. This is the norm of PX. Okay? So the minimum of this cost function is in fact, I don't need the norm here. The minimum of this cost function is in fact the length of this projection. Okay? It's the orthogonal distance between that point and the space that you're looking at, which shouldn't be surprising. That's the smallest you can make the error. Okay? So now let's take a look at what the performance of the least squares estimator is. Let's say we have a model like this, h theta plus error, and I'm going to make the following assumptions. Expected value of E is 0, and let's say the covariance of E is equal to Q. And I'm just going to do a standard least squares. I'm not even going to do weighted least squares. You can by implementing this Q. So theta hat least squares is H transpose H inverse H transpose X. The expected value of the least squares estimator, H transpose H inverse H transpose H theta, and this is equal to theta, so this is an unbiased estimator. Okay? The covariance of the least squares estimate, H transpose H inverse H transpose times covariance of X, H transpose H inverse. Okay? So this simplifies to H transpose H inverse H transpose Q, H transpose H inverse. Okay. So what's important here is, first of all, you got an unbiased estimator. It's a very simple estimator for this linear problem. And even if you don't know the distribution of the data, if all you know is just the mean and the covariance of the error, you can still compute the mean and the covariance of the estimate. There's sometimes a tendency on the part of students to say, well, I can't compute the performance because you didn't tell me that it's Gaussian or whatever. Not true. you can compute the first two moments of the estimate regardless of whatever the distribution is by just following the, just the linear algebra. You don't need any other assumptions. Okay? All right, and of course, as a special case, if this Q is simple, say sigma squared times identity, then the covariance of the least squares estimate becomes sigma squared H transpose H inverse. Okay, so what it tells you is the error in the estimate depends on two things. It depends on the strength of the noise, and it also depends on the condition number of the matrix H transpose H. Okay? So two things can make the estimate worse: pumping the noise up or having an H that is not well conditioned. All right, so if you have an H that is not well conditioned, your least squares solution, even if you do weighted least squares, this term here can blow up and it can give you all kinds of problems. Right? So how do we prevent that? How do we avoid making a big error here by having a covariance that explodes because H transpose H is close to being singular? Now, we did this a little bit before when we did maximum a posteriori, and what you saw was that the way we did it was we made an assumption about the distribution of theta. Okay, so we used the Bayesian approach. We took some distribution for theta and assumed that it was known, and then used that to basically stabilize the problem. And instead of H transpose H, then we had H transpose H plus some other term, and then the whole thing inverse. And that changed the condition number of this guy. Okay, we can do that exact same thing here in the context of least squares, and this is what we call regularized, or sometimes called stabilized least squares. Okay, so the idea here is instead of just minimizing x minus h theta transpose x minus h theta, we minimize this plus another term, let's call it r of theta, which is some kind of penalty on theta. And what I mean by penalty is what's going to happen here, for instance, if H transpose H is close to singular, if there's a slight amount of noise, that amount of noise is going to be blown up, right? And so the size of the estimate that you get, the size of theta hat you get, can become very, very large as a result of noise. So one thing could be, for example, here, you could say, well, I would like to penalize thetas that are very large. So here you could just put the magnitude of theta. I want a solution that has a small magnitude. That's one way to do it. I want a solution that has a small norm of some other kind, not just the Euclidean norm, but let's say you have an L1 norm. Okay? I want the log of the sum of the elements of theta to be small. You can put a number of different things in here. Okay? Each one of them, it turns out, has an interpretation as a kind of maximum a posteriori solution. But this is a very general formulation that doesn't require any probabilistic thinking. It just says, look, just penalize theta so that you limit the range of thetas that you can get. So a few examples. This is of general interest. Is to minimize x minus h theta norm squared plus, say, theta transpose r theta, where this r is simply a symmetric positive definite matrix. Okay, so what this does is if you let r be identity, then this penalty term penalizes the magnitude of theta. But if you let r be some other thing, then it penalizes some function of theta. Okay, that doesn't give equal weight to all the components. Okay, so if you differentiate this, for instance, let's call this j. If we do dj d theta and set it equal to 0, the regularized least square solution is is H transpose H plus R inverse H transpose X, as compared to the standard least squares solution without this term, which was H transpose H inverse H transpose X. And what you see is the difference between these two is this term that's been added underneath that inverse. Okay? So if this guy is difficult to invert because it has eigenvalues that are close to 0, then putting a symmetric positive definite matrix pushes those zeros or eigenvalues away from 0 and keeps them more stable. Okay? All right, what's another way to think about this? Another way to think about this is a maximum a posteriori interpretation of this would be if your data is Gaussian. So if you have x equals h theta plus error, and this guy here is normal, zero mean, and let's say covariance sigma squared times identity, right? Then if you write this distribution down, what do you have? You have e to the minus this term in the exponent, right? So this is basically proportional to e to the minus the norm of x minus h theta squared, right? With the sigma squared in the denominator, 2 sigma squared in the denominator. And if you also assume that theta is Gaussian with zero mean and covariance R inverse, what's the distribution of this going to look like? This is going to look like e to the minus theta transpose R theta, right? With some normalizing coefficient in front, right? Now, if you look at these two, if you multiply these two together, so this is your P of theta, and this would be PDF of x given theta. So this would be maximum likelihood, and adding this would be maximum a posteriori. Then you multiply these two together, what you get is an exponential that has the square error term and this quadratic, okay? Which you're trying to maximize now. That's the maximum a posteriori. So remember, map is you maximize over theta, PDF of x given theta times P of theta, right? This is equivalent to minimizing the exponent, which is exactly that, okay? So this is an interpretation, this is more general. I didn't make any statistical interpretations of this guy. I didn't assume the noise was Gaussian. I didn't assume that theta was Gaussian. Okay? I just wrote this down because it's a reasonable cost function, but this is just another way to think about it. Okay? This is not the only way to stabilize the problem. There are other ways to do it which have similar effect, but the algebra is a little bit different. So let's say, again, I write the least squares problem. H transpose H inverse H transpose X. And now let me write H, which remember is a matrix like this, right? It has more rows than columns. This is P, and this is N. Number of data points, number of parameters. So if I write this as a singular value decomposition, I can write this as U, S, V transpose, right? And this S is the same shape as this guy. And what it's going to look like is there's going to be a square component here, S1 through SP with zeros, and then zeros here. And then V and U are both orthogonal matrices, but of different sizes. So V is P by P, and U is N by N. Okay. So now let's take a look at H transpose H. This is V S transpose S V transpose. So if we write this down in a longhand, this would be the sum over I of SI squared VI VI transpose. Right? I equals 1. Okay? All right, so what's H transpose H inverse in this formulation? Well, H transpose H inverse is simply this thing with this term in the middle inverted. Okay, so if you write it again in terms of the sum of these columns, this is the sum over I of 1 over SI squared VI VI transpose. And remember, these are rank 1 matrices that you're adding together, right? Okay. So if you look at this solution, the place where this solution gives you trouble are places where SI's are close to 0, right? So if you have a singular value that is really close to 0, it's going to get magnified by doing this 1 over S squared. Okay. So one way to avoid this is to cut this sum off before you get to the point where the SI's are too small. Okay. So one way to do it is to approximate this by ignoring some of the i's. Okay. So then you go from sum equals I equals 1 to, let's say, Q of 1 over SI squared VI VI transpose. Okay, where Q is strictly less than P. And what this will do is it will avoid, so I'm assuming that you have S1 bigger than S2 and so on, SP, and let's say this could be bigger than or equal to 0, right? And so this guy could be very close to 0, and maybe the last P minus Q could be very, very small. And so you just avoid them. This is one way to do it. Okay. Another way to do it is to rewrite this sum as the sum I equals 1 to P of 1 over SI squared times, let's put a coefficient here, rho I times VI VI transpose. And this rho I here would be some number between 0 and 1 for each I. So as a special case of this, you would have this guy, right? So the last few i's you're setting to 0, and all the rest of them you're setting to 1. But it doesn't have to be that way. This rho I can be, in this fashion. It could be decaying, like this. In this case here, I've set it to be 1, 1, 1, and then zeros. Okay? And then you can ask the following question, what would be the rho i's such that the mean squared error in your estimate, in your least squares estimate, which is approximated this way, would be as small as possible. Okay. And if you think about it that way, then the solution for the rho i's turns out to be something called the Wiener filter, which we'll talk about a little bit later in the course. Okay. So you can in fact optimize these guys if you know a little bit about the system. All right, sometimes when you estimate parameters, you're also forced to consider a constraint that the parameters have to satisfy. In other words, the estimates cannot be free. So constrained least squares, let's for instance say you have x of n is a bunch of data points is equal to some signal s of n, which has a couple of parameters. I'm going to call them theta plus noise, n equals 1 to capital N. And let's say the signal s of n and theta is equal to alpha n plus beta n squared. So that theta is alpha beta. Okay? And suppose that somehow I am forced to consider the situation where alpha plus beta is equal to 1. In other words, whoever wants me to fit this model has given me the constraint that the coefficients have to add up to 1. Okay? So So this is the constraint. So of course I can write this in vector form as 1, 1 times alpha, beta equal to 1. Right? So call this A, call this theta, and this B. So what I have is A times theta equals B as a constraint. Okay? So now let's write all these equations down in one matrix form. So I have x equals 1, 1, 2, 4, so on, n squared times alpha, beta, plus air. And of course this is my theta, and this is my h, right? And the constraint is A theta equals B, where theta is a p by 1 vector. A is an r by p matrix, and B is an r by 1 vector. In this case, r is just equal to 1. The dimension is equal to 1. It's very important to recognize that this constraint must be such that the rank of A, which I'm calling r here, has to be strictly less than p. Why? Because if the rank of A is equal to p, or greater, then what you're going to have, well, it can't be greater, so if the rank is equal to p, then what happens is that this equation uniquely specifies what theta is. Right? So imagine if A was a square matrix. I give you a square matrix times theta equals a known number, or a known vector. Well, then you just solve for theta. Right? This uniquely gives you, then you don't need the data at all. Right? So the point is, this constraint has to be such that it just specifies a subspace. It doesn't specify everything about the theta. It specifies a space in which theta can live. So this has to be true. Otherwise, value of theta becomes fixed. And so another way to think about this is that what you really have, you have p minus r independent parameters. So if you go back to here, for example, even though you have two parameters you're solving for, what you really have is you only have one independent parameter, because the other one is determined by the first one. The same thing here, same idea. Okay, so how do we solve a problem like this? If we want to do least squares, but we also have this kind of constraint, what do we do? Okay, so what we're solving now is an optimization problem where we want to minimize over theta x minus h theta transpose x minus h theta such that a theta is equal to b. So this is a constraint optimization problem. You're minimizing a quadratic subject to a linear constraint. And so what you're going to do now is again use Lagrange multipliers. And so you construct a new cost function, x minus h theta transpose x minus h theta plus lambda transpose a theta minus b. And this lambda transpose here, these are the Lagrange multiply a vector. You remember, it's not a constant anymore. I'm sorry, it's not a scalar anymore. It's a vector because a theta minus b is a vector. Okay. So what you're going to do now is you're going to minimize this with respect to theta, subject to the constraint that a theta is equal to b. It's kind of interesting to look at this and compare it to what I just called regularization before. Okay, so let me go back for a second. So let's take a quick look at this. So this, if you compare these two, what do you have? You have, this part is exactly the same, right? And this part is not exactly the same, but the whole form is very similar, right? You've got this penalty plus an extra term added to it. The big difference between these two is that this guy does not have to be exactly minimized, right? Whereas this guy, once I'm done solving, has to be exactly satisfied. So this is a hard constraint. This is something softer. Okay, you can think of it as a soft constraint. This is a sort of milder version of this hard constraint that requires an exact satisfaction of A theta equals B. All right, so then we, let's call this J. So we differentiate J with respect to theta first. Minus 2 H transpose X plus 2 H transpose H theta plus A transpose lambda equals 0. Okay? So we solve for theta. We get theta hat. I call it CLS constrained least squares. It becomes like this. H transpose H inverse H transpose X minus 1/2 H transpose H inverse A transpose lambda. So something very interesting happens, namely, if you look at this, this part here is exactly the least square solution without the constraint. Okay? And then you've got this extra bit that you have to deal with. So I'm just going to keep the notation as theta hat least squares because we already know how to do that. What's left over is, we don't know what this lambda is, which is the Lagrange multiplier vector, and we have to solve for it. So to get lambda, we enforce the constraint, which means we write A times theta hat constrained least squares has to be equal to B, right? And then we plug this whole thing in here and we solve for lambda. Okay, so we have A theta hat CLS equals A times theta hat least squares minus H transpose H inverse A transpose lambda over 2 equals B. So this is just this guy here. Okay? And now we have to solve this guy here in order to get lambda. All right, so what do we get? A theta hat least squares minus A H transpose H inverse A transpose lambda over 2 equals B. And then we solve for lambda. Let me just write it as lambda over 2, because I'm going to have to plug in lambda over 2 in here anyway. This becomes A H transpose H inverse A transpose inverse A theta hat least squares minus B. Okay? So now I've got the constraint. All I have to do is take this constraint and plug it in here. Sorry, I have the Lagrange multiplier. I plug it in here and I'm done. So let's write it down. So theta hat constrained least squares is theta hat least squares minus H transpose H inverse transpose A H transpose H inverse A transpose inverse, and then this thing times A theta hat least squares minus B. Okay, so this is the whole expression. It's kind of interesting because if you look at this part, what does this part tell you? Well, this part is just the least square solution without the constraint. Then there's this whole correction term, right? And what's the correction term telling you? This is telling you how far away the least square solution is from, in fact, satisfying the constraint exactly. Right? So if you got lucky and your least square solution satisfied A theta equals B exactly, then there wouldn't be a correction. Right? You can see that here. Make sense? Okay. So just to draw a picture for you, the way standard least squares works, we just saw this. You have a vector x. You make a projection onto the set. This gives you s hat. Right? Now we have something a little different. You also have to satisfy this constraint. So what ends up happening is you have the space, but the space isn't enough. You also have a constraint that has to be, it's also a lower dimensional sort of, let's say a line like this. Okay, so this space is, let's say, two-dimensional. The constraint line can't be two-dimensional. It has to be at least one dimension fewer. And so what happens is if you have a data point here, x, and you project it onto this space, you get this s hat, but it doesn't satisfy the constraint. So then you're again projecting onto the constraint space, and then your solution is in fact this guy. Okay. This guy will satisfy both, it will also live in this space and at the same time satisfy the constraint that you wanted. Okay, so this guy would be s hat, constrained least squares. Okay. Let's see an example. X is h theta plus e. Let's say h is like this. 1, 0, 0, 1, 0, 0. So in this case, just notice rank of h is equal to 2. And it's also true that h transpose h equals identity, just so happens that way. And suppose I want the two parameters, theta 1, theta 2, sum up to 0. I want them to be negative of each other. Okay, so if you solve theta hat constrained least squares, you get theta hat least squares, and you plug in all of these terms that I noted here. So this is A, this is B, and this is your H. So you get this minus 1, 1 times 1 half theta 1 hat minus theta 2 plus theta 2 hat, where these two are in fact the least squares solution. So these are just components of theta hat least squares. So I've skipped over all the simplifications. So if you plug this in, you get 1 half theta 1 hat minus 1 half theta 2 hat and 1 half minus 1 half theta 1 hat plus 1 half theta 2 hat. And these are components of the least square solution. So you can see here, if you in fact add these two together, you get 0, which is what the estimate requires. Okay, questions?
Yeah, can you go back one page, please?
One page, okay. Yeah.
Okay, thanks.
All right, so far, what we've looked at are matrices H, we've looked at this model, h theta plus error, where h has the following shape. It's like this, where this is n and this is p. And we've had either n is bigger than p or n is equal to p. So if n is equal to p, then you have a square system. Right? This matrix becomes square. Then H transpose H inverse is just, you can just invert each term. Things become very simple. H transpose H, so in this case, H transpose H inverse H transpose X is just H inverse X. Okay. In this case, of course, it's not. So here you have more measurements than you have unknowns. We generally refer to this case as the overdetermined least squares problem. Overdetermined because you have at least as many equations, if not more, than the parameters that are unknown. There are situations, however, in which you have fewer equations than you have unknowns. So what about the case when n is less than p. Okay, what can you do? This is called the underdetermined case. Underdetermined because you have fewer equations than you have unknowns. Well, if you have fewer equations than you have unknowns, then in this case, x equals h theta can in fact be exactly satisfied with infinitely many thetas, right? Because there's a whole space of thetas that will make this exactly true. Right, so this will be satisfied with infinitely many thetas. So you can't use the formulation that we just used. Okay. Well, first of all, you can just look at this. H transpose H will be rank deficient, period. Right? So in this case, in the underdetermined case, H will look like this. Right? Where this is your number of samples, and this is your number of parameters. Right? What's H transpose H going to look like in this case? It's going to be a large matrix of dimension p with rank at most n, which is less than p. So you can't invert it. So this is simply not going to work. Therefore, what you're going to need is you need some other constraint, some other force to uniquely pick one of the thetas that is going to make this equation true. So as we just said, there's infinitely many of them that'll work. So you just want to pick one of those. Okay? And there are many, many different ways to select that one solution that you want. The most popular one is to select the smallest solution, the smallest in terms of magnitude. And that's the so-called minimum norm solution. Okay, so which theta to choose? A popular choice is theta such that theta transpose theta is small, or as small as possible. Now, in order to make matters simpler, we put a 1/2 in front of this, because when we differentiate, we want the 1/2 to go away. Okay? So let's see how this works. Okay, so what you want is you want theta to minimize 1/2 theta transpose theta such that x equals h theta is satisfied. Okay, so these are all the solutions. This is going to pick out one of those solutions. And the way you do this is, again, Lagrange multipliers. This time, the j that you define is going to be 1/2 theta transpose theta plus lambda transpose x minus h theta. Okay. By the way, there is, just with any optimization problem which has constraints, there is something called a dual formulation that you can consider. In other words, here we've minimized this guy such that this is true. We could have turned it around and said, I want to minimize this guy such that this is a constraint, then we would have to set that equal to a constant. Okay? Here we don't do that because this guy actually has infinitely many solutions. So you can always take an optimization problem and replace the constraint with the thing that you're trying to minimize. And you should get the same answer, because what happens at the end is, at the end, you're going to write a linear combination of these two things like that. Right? So the only difference is you either put the lambda here or you put the lambda there. You get basically the same function to minimize. All right, so then we differentiate this. Ej d theta, theta plus h transpose lambda equal to 0. We solve this for theta hat. Theta hat is minus h transpose lambda. Now we need lambda, and for us to get the lambda, we need to invoke the constraint, which is x has to be equal to h theta hat. You plug things in, you get minus h transpose lambda. So lambda is equal to minus HH transpose inverse times X. Now here, what you notice is that you get HH transpose instead of H transpose H. HH transpose is now going to be a matrix of size n by n, which is going to be full rank. Okay, I'm assuming that this matrix here is full rank. The H is always full rank. Okay, so if you plug everything in, plug this lambda into this expression here, the minuses cancel out. And so what you get is theta hat becomes H transpose, H transpose inverse X. So let's remind you again that X is an n by 1 vector. This H transpose H inverse becomes an n by n matrix. And the H transpose here is P by n. So everything makes sense. This whole thing on the right-hand side is P by 1, which is the dimension of theta hat. Okay? So this is the determined system. Let's just compare that to the overdetermined system. It's H transpose H inverse H transpose X. This is the overdetermined case. So take a look at these two. It's easy to confuse them. That's all I have to say. Okay? Just make sure you don't confuse them, because one will simply not make any sense in the other case. Okay? In this case, you couldn't do H transpose H because it's not invertible, and in this case you couldn't do H transpose, it's not invertible. Again, I want to emphasize that this particular manner of nailing down one of the solutions is completely arbitrary. But it makes the solution very easy to compute. You could pick some other function to put in here, some other f of theta. Okay? And as long as you can minimize f of theta plus this constraint and carry it through and get an answer, that's fine. Okay?
Excuse me.
Yeah.
Why don't you consider the noise term here in the overdetermined?
Are you talking about
No.
in
This
here?
state, yes.
Well, the point here is that because of the dimensions of H, even if X has noise in it, you could still pick theta to exactly satisfy this equation. Do you see what I mean? So you can just forget about it, okay? Because you have all this open sort of null space where you can fit the information. Whatever noise you end up adding to this, the extra parameters will take care of it. You can perfectly fit to the noise. Nothing there. Okay? That's why I just essentially ignore. But it's a good question. Okay? And in fact, that may be a reason, depending on how your noise is behaving, you may want to have a different property for the theta that you eventually come up with. All right, so in this case, I happen to pick a quadratic term to penalize, to pick out a particular theta. But maybe in the particular model that you're dealing with, you don't want that. You don't want to get the minimum norm solution. There's another name for this. It's called the minimum norm solution. Maybe you want the minimum entropy solution. Right? You can compute the entropy of the vector theta, use that in this term here, and solve it. That's entirely possible. You might want the theta which is sparse. Okay? Has anybody heard about sparsity? It's a very, very popular topic nowadays. You want to come up with a vector theta that has as many zeros in it as possible. So it has lots of zeros and a few spikes. Okay? Those are called sparse matrices. So what you do is then you write theta in a basis. Right? You write theta equals some basis k times a bunch of parameters, and then you say, okay, these parameters have to be mostly zero. So you can do that here as well. Okay?
You mean the noise component can be explained in terms of the plane that...
That's right. That's right. The noise component can be explained because it can be explained exactly every time, because the dimension of the space that you're dealing with, this H, is much larger than the amount of data that you have. Okay? So let's look at the shape. If you look at the shape of this, okay, what you have is the rank of this matrix is at most n, right? But you have p different vectors that you can play with. So if I give you a bunch of noisy data, you can explain that data exactly because you have so many degrees of freedom. Okay? And that's a bad thing, right? Because the noise is supposed to be gotten rid of. It's not supposed to be explained, right? And so that's why you want to pick a particular value of the theta as an answer, because there's so many choices to exactly describe the noise and the data that you've got. Okay, other questions? All right, so the next thing we're going to do in the next maybe 20, 25 minutes is to talk about doing this least squares in a sequential fashion. What do I mean by that? So far, everything that I've talked to you about has been what we call a batch process. In other words, I give you a bunch of data, x1 through xn, and you take all of this data at once, and in one shot you compute an estimate. Okay? Much more common is the situation where I give you a bunch of data, you compute an estimate, and then I give you one more data point. Okay? And then the next day I give you one more data point. Or 10 minutes later I give you one more data point. So what should you do? Should you take all this data that I gave you, add the one more data, and do your estimation all over again? Well, you could do that. But computationally, that's not a very smart thing to do. So an alternative to this is I give you a bunch of data. Let's say to start, I give you 10 data points. You take these 10 data points, you compute an estimate. Then I give you an 11th data point. And instead of doing the whole thing over again, all you do is you take the estimate that you have, you update it. In some clever way, you simply update this using the new information that you got. And you repeat this process. And this is called the sequential estimation. Okay, so let's see a very, very simple case of how this works. So let's say I have sequential or recursive least squares. By the way, this can also be done with all the other estimators that we talked about, with maximum likelihood, with maximum a posteriori. All of these estimates can be done in this fashion, in a sequential fashion, except that the equations will be a whole lot messier. Okay? And if you do them in the general fashion that we talked about, then you end up with things like the Kalman filter, which some of you may have heard about. That's nothing but a sequentially updating estimate, which is optimal at every step. All right, so let's take a look at this in a very general sense. Suppose we have, so here's an estimator, and it pops out an estimate. Suppose we have x0 through xn minus 1. And now, I suppose I give you another data point, xn. Then what do you do with this? How do you update it? Okay, so let's take a very, very simple example as our building block and see where we can take it. So suppose we have this this problem where A is the unknown, and this is the only assumption I'm going to make. Okay, so suppose I have data for n equals 0 to capital N minus 1, and I do least squares. I get A hat is equal to 1 over n sum n equals 0 to n minus 1 x of n. It just gives me an average of these guys, right? I want to give this A hat an index because it's using data up to point n minus 1. So I'm just going to give it a subscript. Let's call it n minus 1. Okay. So now let's suppose I give you a new data point. So now I have n equals 0 to capital N, and I do least squares again. I get A hat. This time I put subscript n. This is 1 over n plus 1 now, sum n equals 0 to n of x of n. Right? And the point of what I just told you earlier is that I want to avoid having to do this all over again. And so let me see if I can, by just massaging the equation, somehow write this guy in terms of that guy and see if it works. It turns out it's not very difficult to do in this case. Okay? In general, it may be much more complicated because the estimator may not be linear. Right here, the estimator is very linear. Easy to do. In general, it won't be. So a hat n is 1 over n plus 1. And the sum n equals 0 to n minus 1 x of n plus x of capital. Okay? So all I've done is I've simply written this in terms of two pieces, one that looks just like that and another one which is the new data point. And so this is 1 over n plus 1, n times a hat n minus 1 plus x of n. Okay? And then I'm just going to massage the equations and simplify things, and then what I'm going to get is this. A hat, so n is a hat n minus 1 plus 1 over n plus 1 times x of n minus a hat n minus 1. Okay? Let me move this up so you can see a little better. Okay? This is just algebra, just a few steps of algebra. And so let's take a look at this and see what happened. What happened was the new estimate is the old estimate plus a correction. Okay? This is somewhat similar in spirit to what we just did with the constrained least squares, right? So you had the constrained least squares is the unconstrained solution plus a correction. And this is exactly the correction that you have. Let's see what this correction in fact does. What is this? What this is basically is measuring how different your new data point is from what you expect it to be. Okay? If you had no noise, what would you expect your data to be? Hey, this would be 0, right? So the difference between xn and a hat, which is the estimate, is the error that you expect to have, right? That's exactly what this is. Okay? And there's something in front of it. This is called a gain, and we can talk about that in a minute. This is what we generally call the prediction error. So let me be a little more explicit about this. So let's write xn minus a hat sub n minus 1. So this is xn minus 1 over n sum n equals 0 n minus 1 of xn. This is just another way to write this, right? So what this is you've got all this previous data and then you've got the new data. And what this is doing is it's measuring how much error there is in predicting the new data point from the old data points. Okay? Okay, it's also interesting to look at the least squares cost function and see how it kind of goes down as a function of iterations. And in other words, as a function of this index n. So if we look at the minimum of least squares cost, well, if you have n minus 1, data up to n minus 1, then the minimum of the least squares cost is the sum n equals 0 to n minus 1 of xn minus a hat n minus 1 squared, right? And the next point, sorry, n, is the sum n equals 0 to n x of n minus a hat n. Okay? And I can then manipulate these two equations and write one in terms of the other, and so on and so forth. I'll spare you the algebra, but basically I can write this minimum in terms of that minimum, and I want to show you kind of what it looks like. So the minimum of the least squares cost after n data points is the minimum of the least squares cost after n minus 1 data points plus an extra term, which is n over n plus 1 times xn minus a hat n minus 1 squared. Okay? Why am I writing this? I'm writing it because at some point you will be asked to write it yourself, and in all likelihood you'll find this confusing because what you see is that somehow you're getting a new cost function which is larger than the old cost function even if you have more data. Right? So the idea is if you get more data, you should somehow you would expect things to get better, right? But here your cost is increasing. You've got this plus a positive number. Why is it increasing? Why is this not decreasing as you get more data points? Well, the answer is very simple. And the simple answer is that we define this cost function without putting a 1 over n in front of this. Okay. So we define the cost as the sum of the squared errors. It's the mean squared error. If we had put a 1 over n in front of this, then you would see a different behavior here. Okay. So don't worry about this kind of looking like it's getting bigger because you're actually adding more terms and this behavior shouldn't be too disturbing. All right. So now let me go back to this equation here. Let me go back to this equation here and write it in a very general form and explain to you what each of these terms in fact mean. Well, let me start with the top of the page. So a hat after n samples is a hat n minus 1 plus k of n, which is what I call the gain. In this case, it was 1 over n plus 1. X n minus a hat n minus 1. This is supposed to be sub n minus 1. Okay, so this we call a gain. This we call the innovation. Another way to call it is the prediction error. Okay, in our case, we just assumed that the noise was zero mean, and this is what we got. Now, if you make the assumption that the noise is zero mean and its covariance, or variance I should say, of W is sigma squared n, and their IID, okay? So each sample is zero mean and it's got variance sigma n, and this n can change, right? So the variance doesn't have to be the same from sample to sample. So if you write all of this down and you do the same analysis that we did step by step, what you'll see is that this equation remains exactly the way it is, with the exception that the gain becomes like this. K of n becomes 1 over sigma n squared divided by the sum of 1 over sigma n squared, n equals 0 to capital N. Okay? And now, if all of these sigmas were the same, then this would just be 1 over n plus 1, just like it was before. Except that now you get different weights because of each sample doesn't have exactly the same weight associated with it. Another nice thing about doing this is that it allows you not only to update the estimate itself, but it also allows you to update the variance of the estimate. Okay? So you are able to carry forward the estimate and the level of uncertainty about that estimate at every iteration. In particular, so let me write down the variance of a hat sub n minus 1. So this is going to be the variance of, if you do all of this, sum n equals 0 to n minus 1 x of n over sigma n squared, and the sum 1 over sigma n squared equals 0 to n minus 1. Okay? Simplifying this, we get 1 over the sum 1 over sigma n squared. Okay? So this would be the variance for this particular estimate at that iteration, and then we can go to the next one, and what we will see after n samples is exactly the same form, 1 over the sum, n equals 0 to n this time, 1 over sigma n squared. Okay? So again, these two are related to each other in a way that one can algebraically express. It turns out what we get is the variance of a hat n is 1 minus kn times the variance a hat n minus 1. Okay. Now a couple of interesting things happen here. If you look at this, despite the fact that when we computed that function j, we observed this weird behavior, what this tells you is what happens to the uncertainty in the estimate of A as you get more and more data samples. Intuitively, what would you expect to happen? You would expect the variance of the estimate, as you get more and more data samples, the variance to collapse. Right? Eventually you get a perfect answer with sufficiently many data samples. Right? So if you look at this expression, if I now look at some large n, what happens? I would want to see with every new data point an improvement in the variance, right? And so what would happen is that's going to happen only if this term is less than 1, right? And you can see that it's true here, and in fact it turns out it's true in general. So we just did this for this very simple example, but the idea here is that by looking at this, you see there's a stable nature to this iteration in the sense that the next data point that comes in, because of this guy being less than 1, it will give you an improved estimate. Okay? All right, now, yeah.
So why did you write the j function that way, and you didn't insert the 1 over n factor?
Well, the reason why we write the j function in that way is because that's just the way we define the least squares criterion. Let me go back here. This is just the definition that we used from the beginning. So I'm just showing you that there is something that can be slightly confusing about the way you define this. The other thing that happens is that in general, when you write something like this is the mean squared error, which means that it's the variance plus the square of the bias, right? What I'm showing you here is only an expression for the variance. In general, you might end up with a biased estimator as well. In this case, you don't, because this problem is very, very simple. It's just a linear single parameter estimate. But in general, you might have a variance that's nicely decreasing, but your bias might be marching upwards. Okay, so those two things balance, and they give you these expressions for the mean squared error. So what I'm going to do next time, I don't have enough time to set this up, so I don't want to get too complicated about it right now, is what we're going to do next time is to consider a very general least squares problem where we think of x minus h theta transpose c inverse x minus h theta, and what we're going to have is your vector x is going to be x0 through let's say xn, and then what we're going to look at is what happens if this x then has one extra element in it. Okay, if you then add one extra element to this, so you add one more, let's say xn plus 1, what's going to happen is that the size of this matrix H changes. Okay, so every time you add a new data point, you have to add an extra row to H. Right? So then what we're going to do is we're going to take H and look at it as the old H concatenated with an extra row, and then we're going to break that problem up and show you that the structure of the estimator that you get is very much like what I just showed you here. The linear algebra just gets more messy. Okay? And all of this is just for linear estimation problems. And this is still a linear estimation problem because this is a linear model of the signal. Right? All of these things can also be done as, we unfortunately don't have too much time to get into that, but they can also be done for nonlinear problems. Okay? The way they are done for nonlinear problems is that they, basically you take a nonlinear problem where h theta is no longer just a linear thing, it's like SAS of theta, and you linearize. Okay? You approximate S of theta with something like h times theta, and then when you get an estimate, you reapproximate, just like we did before for the iterations, and at every step, in addition to adding a new data point, you have to relinearize the problem. Okay? But this is basically the general framework for things like the Kalman filter. Okay? Iteratively or sequentially improving your estimate every time a new data point comes in without having to do everything all over again. All right? So we'll stop here. Any questions? No? Okay. We'll see you next time.